Hello and welcome to another session in physics. In this session, we'll be looking at the topic crystal structure of matter under amorphous and crystalline substances. But before that, let us review the previous lesson. Welcome back. Now let's talk about crystal structure. The term crystal structure is generally used to describe the internal structure of solids. Remember, we said matter is divided into three states: solid, liquid, and gases. And we said liquid and gases are classified under what we call fluids. Solids have strong intermolecular forces, as we also discussed last time out. And then we said liquids have intermolecular forces that are not so strong as that of solids, and gases on their own part have the weakest intermolecular forces because the molecules that make them up are so far apart from each other, but that they possess sufficient pressure. So you would notice from the diagram here that the particles of a solid are arranged orderly in parallel planes. So in other words, solid crystals consist of particles arranged in parallel planes. When we talk about crystals, we talk about simple structural units that have been built up using what we call unit cells. Yes, crystals have foundations. The foundations are called unit cells. What is a unit cell? A unit cell, which is also known as a space lattice, is a cell that is made up of a few atoms, a few ions, or a few molecules. They make up what we call a unit cell, which makes up these crystal structures. Now we have 7 such types of crystal structural systems. We have the cubic structural system. The cubic structural system, that is the one you see here on the slide, the first one here, the cubic structural system. And then of course we have the rhombic structural system. We have the rhombic structural system. The rhombic is the one we call here orthorhombic, or the rhombic structural system. This is what it looks like. And then we have the monoclinic structural system. Monoclinic structural system is this one. It looks like this, slanting to the side. And then of course we have the triclinic structural system. Triclinic structural system looks more like an inverted cuboid. Triclinic structural system. And then we have the tetragonal structural system. Tetragonal is this, looks more like a standing cuboid. Tetragonal structural system. And then we have the rhombohedral structural system. The rhombohedral structural system looks like this, more like a side view from up looking at a standing cuboid. Rhombohedral structural system. And then we have the last one, the hexagonal structural system. Counts them 1, 2, 3, 4, 5, 6, 7. So these are the 7 such types of crystal systems that we have. Remember, we said the crystal systems are unit cells made up of atoms, ions, and molecules, which make up the internal structure of solids. Now, crystal systems are made up of imaginary lines of symmetry that form angles. Yes, these angles are what help us to determine the system to which a particular crystal belongs to. The angles help us to determine the particular system to which a crystal belongs to. Now, this is also a further diagrammatical representation of these structures. So take your time. At the end of this video, you can pause and go back a little bit and study these structures once again. We have the simple cubic, the body-centered cubic, face-centered cubic, simple tetragonal, body-centered tetragonal, simple orthorhombic, body-centered orthorhombic, base-centered orthorhombic, face-centered orthorhombic, rhombohedral, hexagonal, simple monoclinic, base-centered monoclinic, and triclinic. So take your time and go through the structures, look at them critically, and see how the angles they form help us to identify the particular systems a crystal belongs to. At this point, let's talk about the differences between crystalline and amorphous substances. On the basis of the internal structure of a solid, it is actually possible for us to classify whether a solid is a crystal substance or whether it is an amorphous substance. When we talk about crystal substances, we mean substances that have definite shape. And then when we talk about amorphous substances, they are not so definite in shape. We call them shapeless. So look at the structure here. Crystalline substances, they are more definite because the intermolecular forces binding them together are so close knit. So it gives them a definite shape. But amorphous substances are a little bit shapeless. They don't have definite shape most of the times. We'll look at these differences between them in the subsequent slides. Crystal substances are examples. We have common salts, and under amorphous substances we have particles of glass moving them together. Alright, so at this point, let's look at some of the differences between crystal and amorphous substances. Differences. Between crystalline and amorphous substances. So you can call it crystalline versus amorphous. So let's call this crystalline, and then let's call this one amorphous. So we're going to try to see the differences between two of them. Well, when we talk about crystalline substances, like I said earlier, the first one is that they have definite arrangement. They have definite shape. Here, they don't have a definite shape. And then the second one is that the crystalline substances have cleavage planes. They have cleavage planes, and these ones also don't have cleavage planes. The crystalline substances, they meet sharply at definite temperature. They meet sharply at definite temperature, whereas these ones don't meet sharply at definite temperatures. And of course, they are regarded, crystalline are regarded as true solids. They're regarded as true solids. These ones are not regarded as true solids. And then the next one is that they have a long range of order of arrangement. Crystalline substances have a long range of order of arrangement, whereas amorphous substances have a short range of order of arrangement. Interestingly too, crystalline substances are efflorescent in nature. They are efflorescent in nature, or we can say they are efflorescent substances. These ones are not efflorescent substances. So these are the basic differences between crystalline substances and amorphous substances. So do take your time to look at that as well. Now let's talk about surface tension. When we talk about surface tension, we are talking about the property that a liquid has to make its surface behave as though it is covered by an elastic skin. Make it look as if it is sticky. Sometimes you go to the borehole or the tap to fetch some water. When you fetch this water, you discover that some droplets of liquid drop from the mouth of the tap. Those droplets of liquid, watch them critically when they are trying to drop. It's as if they are stretching, they are sticky, or they're trying to be elastic. That is what we call surface tension. Surface tension is defined as the force per unit length of the substance, and it is given by F over 2L. Surface tension is also the force that acts parallel to the surface of the liquid in question. Some effects of surface tension is in the formation of soap bubbles, which are spherical in shape. Those soap bubbles are spherical in shape. That's an effect of surface tension. Surface tension also makes it possible for water skaters to be able to walk on the surface of water. You see those who are doing jet skiing, so on and so forth. We also have a razor blade or a needle when you get a razor blade or a needle and you place it gently on the surface of the water, it will surely float, despite the fact that it is a metal and should naturally sink down below the water. But it will float when you place it gently. That is also an effect of surface tension that is behaving as an elastic body at that point in time. Also, spilled mercury on a glass surface forms spherical droplets. Now, let's look at the application of surface tension. One of the applications of surface tension is in the manufacturing of rain-proof clothes or materials, or waterproof. Sometimes we have the ones we call raincoats. Raincoat helps in preventing rain from touching our body when it is raining and you have to go outside. So it is one of the applications of surface tensions. It is also used in the absorption of ink with blotting paper. Also helps in the rising of oil in lamp wicks and in the movement of melted wax into the neck of a burning candle. Interestingly, it is also used in the construction of umbrellas. Have you ever wondered how it is that water does not penetrate the inside of an umbrella even though it is raining outside? That is an application of surface tension that makes the umbrella behave like an elastic skin and prevents water from permeating its surface. Now, what are some ways that we can reduce surface tension? One of the ways that we can reduce surface tension is by the addition of impurities such as detergent, soap, alcohol, oil, camphor, kerosene, and grease. So these are impurities that we can introduce into a system and will help to reduce surface tension. Additionally, if you want to reduce surface tension, you can also heat that liquid. For more information, visit the material attached to this video. Thank you for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear soon on your screen.